Maths Aspirants is a collective of mathematics students, research scholars, and teachers across India, initiated by myself in 2017. And we used to arrange online problem-solving sessions and online test series to help the students who prepare for different national competitive examinations. As all of you know, TIFR GS 2023 examination is on next Sunday. And this year, we have planned to arrange 3 exclusive online problem discussion sessions for TIFR exam. And we already had 2 sessions, and today's is the last in that sequel. Today, we have Miss Jiya Johnson, a research scholar from IIT Madras, is with us to engage the session. I'm very happy to introduce Jiya. Jiya was a member very since its beginning, and she did her MSc from CUSAT, Cochin University of Science and Technology, and qualified GATE as well as CSAR, and then currently pursuing PhD at IIT Madras. So I would like to express my gratitude and thanks to Jiya for being with us, and I welcome everyone to this session. Hope that today's session will be really helpful in your preparations, in your final preparations for TIFR exams. Welcome everyone. Welcome, Jiya.
So thank you. Thank you for inviting me. So next week we will have the TIFR exam. So we are in a final lab. So we will. It will be mostly based on problems. We will not get much time to discuss the theory part, but still we will tell the necessary theory in corresponding to each questions. So we will start soon, and I expect your participants, your contributions as well. It will be like a discussion. So you can interact in between. If you have any questions, you can pose it. Okay, so then we can start now itself. We will be discussing the problems from last year, 2022. So as you all know, there are 2 types of questions, MCQ and true or false. So first we will discuss some MCQ questions and later we will move on to true or false questions. So first question, consider the following properties of a metric space XD. XD is complete as a metric space for any sequence Zn of closed non-empty subsets of X such that Z1 is a superset of Z2 is a superset of etc. That means Zn is a nested sequence of closed intervals, and limit n tends to infinity, supremum of xy belongs to Zn, distance between x and y. That is a diameter of Zn. So limit n tends to infinity, diameter of Zn is going to is 0. Then intersection Zn is a singleton set. So these are the 2 statements regarding a metric space, and which of the following sentences is true? 1 implies 2 and 2 implies 1, 1 implies 2. So we have to check. So have you familiar with any theorems related to this? Or what is the job?
Intersection.
Yes, very good. The first part is directly the Cantor's intersection theorem. So what is the geometrical idea you have? That is, we have, first we are assuming XD is a complete metric space. And we have a sequence of closed subsets such that Z1 is a superset, like that it is going on. That means, can you just see this scenario geometrically? So this is Z1. Z2 is lying inside Z1. So this is Z2. This is Z3. And this diameter of Zn is tending to 0. So it is becoming smaller and smaller and smaller. Okay. Now, suppose the first part is, we can try. That is, first is, if XD is a complete metric space, then for any sequence, this will satisfy. This is, as you said, Cantor intersection theorem. But those who don't know the theorem, we will just revise the idea of the proof. So we have to show that intersection Zn is singleton. So the only thing we know is XD is a complete metric space. XD is a complete metric space means every Cauchy sequence is convergent. So can you find out, or can you get a Cauchy sequence from this picture? And we know that each Zn is non-empty. So can you choose a Cauchy sequence from this figure?
Choosing one element from each set.
Yes, exactly. So we can choose one element, say some x1 from z1, some x2 from z2, some x3 from z3. Like that we can choose. So these elements will be going like this. Okay. So this will be a Cauchy sequence. And this Cauchy sequence is convergent. So consider our Cauchy sequence as xn. Then since the space is a complete metric space, this xn will converge to some element x. So what is the obvious choice of what is your intuition of this intersection Zn? What will be that intersection Zn? Can you guess it?
Singleton set X.
Singleton set X. Very good. So this xn will converge to x, and this x will belongs to intersection Zn. Why? That is, we have to show that x belongs to set k for all k. Suppose x does not belongs to some set k, then what does it mean? X is lying somewhere outside that set k. So this set k is a closed set, and x is lying outside that closed set means there exists a neighborhood of x which is completely contained outside set k. So in this neighborhood, all the remaining terms are lying here. So in this neighborhood, we cannot find any terms after a finite stage. So this xn cannot converge to x. So the only possibility is x should belongs to intersection Zn. Now we have to show, so we got that x belongs to intersection Zn. Now we have to show that x is the only element in intersection Zn. What happens if we have two elements, say some x and y? So our x lies here, y lies here. And we know this x belongs to all intersection Zn and y also belongs to intersection Zn. So if we take a small neighborhood of like this, and we know that x belongs to Zn for all n. That means all the Zn's are coming like this. And here all the Zn's are coming like this. So ultimately what is happening? So we have created a Cauchy sequence, and here I have proved that the Cauchy sequence is this is a Cauchy sequence, and since xd is a complete metric space, this Cauchy sequence converges, and then we claimed that this x will belongs to intersection Zn, and then we have to prove the uniqueness. So if xy belongs to intersection Zn, then distance between xy will be less than or equal to distance between x comma xn plus distance between xn comma y, and which will be less than or equal to 2 times diameter of Zn, because this x belongs to intersection Zn. So x belongs to Zn, xn will belongs to Zn. So both x and xn belongs to Zn. So its distance between x and xn will be maximum diameter of Zn. Similarly, this y belongs to intersection Zn. So in particular, y belongs to Zn, xn belongs to Zn. So distance between xn and y will be again maximum diameter of Zn. So, and this diameter of Zn is going to 0. So this distance between x and y will be equal to 0. That means x should be identically equal to y. So this is Cantor's intersection theorem. Now we have to check whether the converse is true. That is, suppose if we have a family of nested closed sets, and if it's suppose for given a closed set, a family of closed set such that it is a nested family, and its diameter is going to 0, and its intersection is a singleton set, then is it true that XD is a complete metric space? So in order to show that XD is a complete metric space, from where should we start? We should start with a Cauchy sequence in XD. So let AN be a Cauchy sequence in XD. Now, we have to use the second part somehow. So we have to construct a nested sequence of Zn using this Cauchy sequence. So can you construct a nested sequence of closed set Zn using this Cauchy sequence An? Hello?
Yes.
How you will construct? So we have a sequence, a Cauchy sequence An. We have to construct a nested sequence of Zn such that it should come like this. This is etc. Like that it is moving on. So what if I choose Z1 is equal to A1, A2, A3, etc. the whole closure. Z2 equal to A2, A3. We will avoid the first term and we will take the closure. Likewise, Zn equal to An, An plus 1, etc. the whole closure. So here each Zn is a closed set, each Zn is non-empty, and we have Zn is a superset of Zn plus 1, and its diameter of Zn will be going to zero, right?
0.
Because it is a Cauchy sequence. So that you can use this epsilon epsilon definition plus epsilon that you can use, and we will get this diameter of Zn will go to 0. So by our converse part, we know intersection Zn is a singleton set. So call it as some A. So what is your guess? What is your intuitive idea? So here we have constructed a sequence of closed sets. And then, can you guess? Now, can you guess the limit of An?
A.
A. It will be A. So now, can you prove it? Sorry. So our claim is An converges to A. So how you can prove that? Suppose we are taking an epsilon neighborhood of A. Then this A belongs to intersection of Zn, and this Zn, diameter of Zn is converging to 0. So there exists an n belongs to natural numbers such that diameter of Zn is less than epsilon for all n greater than or equal to n. So all such Zn, and A belongs to that Zn also. So A plus, or you can just take it as some epsilon by 2. So this is A plus epsilon by 2, and this is A minus epsilon by 2. So A belongs to Zn, and diameter of Zn is less than epsilon by 2. So this Zn will be lying somewhere here, and Zn plus 1 will be lying somewhere here. Okay, likewise it is happening. So all the ANs after this stage n, this belongs to this epsilon interval. So from that we can conclude that AN converges to A. Okay?
Yes, ma'am.
So that you can prove it. So the answer is both implication we have 1 implies 2 and 2 implies 1. And the thing is, when you do the problems from the previous question, you can start thinking in a neighborhood. That means here the question is XD is a complete metric space. Then this if Zn is a family of closed sets, that all these things happen. So you can ask other related questions like what happens if XD is not a complete metric space? Will this theorem hold? Or can you give a counter example? So can you give a counter example? If XD is not a complete metric space, then the second condition need not be satisfied. Say, for example, if we consider open interval 0, 1 in R, and if we consider the subspace topology, the family of closed sets. And we have this, call it as some Zn, and we have all the properties. Each Zn is empty, each Zn is non-empty. Zn is a superset of Zn plus 1. Diameter of Zn is going to 0. All the conditions we have. But what will be intersection Zn?
Empty set.
That will be an empty set. So if X is not a complete metric space, this theorem need not hold. Okay, likewise, you can ask some other questions. What if diameter does not converge to 0?
Then it may not be singleton.
Yeah, it may not be singleton. For example, if we take intervals like, this is 1.
0, 1
Yeah.
plus 1 by n.
Yeah. You can, 1 plus 1 by n. You can consider intervals like this. So this will be the first one. Second one will become smaller and smaller. And the intersection will be this closed set. So this intersection need not be singleton in that case. Okay. So then what if closed sets are replaced by open sets? Can you give a counter example? Suppose if XD is a complete metric space, and if we have a family of open sets satisfying a nested sequence of open set, then does it ensures that intersection will be a singleton set? Can you give a counter example? We have set this example. You can try from this itself. You can adjust. That is, if we take 0, 1 by n. So these are the family of open sets. And intersection 0, 1 by n will become an empty set. So it need not be singleton set. So likewise, you can ask several questions related to one question. If you solve one question, it is not only that question. You have to think in a neighborhood, the possibilities of other questions. Okay. So likewise, you can add your own questions to each question. So this I told you just to say that how to think related to a question. But we cannot add these questions to in the remaining question because we have the limitation of time. But you can think when you work out problems and all, you can just think in this way. Okay, so we can go to the next question. Consider the following assertions. XY belongs to R2 such that XY equal to 1 is connected. XY belongs to C2 such that XY equal to 1 is connected. So we have to find which one is true and which one is false. Okay, so can you visualize the first one? Before that, what is the definition of connectedness? Maybe BSc students will not be knowing. A set is said to be connected if it cannot be written as the disjoint union of two open sets. Okay, so now can you just visualize this first one? At least the first one, can you visualize it? What is it? What is that graph? So what will be this graph? Y equal to 1 by x, right? So the elements will be union of these two curves. So is it connected or not connected? Hello?
Not connected.
Not
Not
connected.
connected.
Okay. Now, what about the second question? Here, xy belongs to C2, so it is bit difficult to visualize it because we have to be in at least in fourth dimension, such that xy equal to 1, which is, so we have to check whether this is connected or not connected. So if we take 2 points from C2, so here the condition is xy equal to 1, and we are taking the collection of ordered pair xy. So the terms will be x comma 1 by x. Each element will be. So if we take two elements from C2 from this family, that is x comma 1 by x, y comma 1 by n. So is it possible to, and we know that path connected will imply connected. So path connected means we should be able to find a path between any 2 points. So we took arbitrarily 2 points. So if we are able to connect these points, then we can say the set is path connected, and path connected will imply connectedness. So is it possible to construct a path between these 2 points? So we don't know, we are not sure. So I'm reducing my question to, is it possible to find a path between x and y in C? So you have two complex numbers x and y. Is it possible to find a path between x and y? Path means a continuous function from closed interval 0, 1, such that that path, if that map, that continuous function, if we call it as p of 0 equal to x and p of 1 equal to y, that is path. So is it possible to find a path between x and y in C? So suppose this is our C, and we have 2 points x and y. Tell me.
Not possible.
What?
Not possible to find path.
From if we take 2 points from C, this is x, this is y. These are two complex numbers. So path means ultimately we have to find a way. What?
Ty plus 1 minus tx, it will be a continuous path.
Yeah, you are connecting x and y. So that will be a continuous path. And we can find any path, continuous path. This will be a continuous path. Like that, we can create many continuous paths from x to y. So now we have a path connecting x and y. Say it as gamma. So now that is gamma of t is gamma is a function from closed interval 0, 1 to c, such that gamma of 0 equal to x and gamma of 1 equal to y. So now can you try connecting these points x comma 1 by x and y comma 1 by y? So that path will be, so that path P will be a mapping from closed interval 0, 1 to not C2, that that subset of C2, such that xy equal to 1. So what will be the obvious choice of path? Some P of t. We have gamma of t connecting x and y. So now connecting 1 by x and 1 by y, what is the obvious choice of path coming to your mind? Hello? Hello. So we have a path connecting x and y. That is gamma of t. We have to try get a path connecting 1 by x and 1 by y. So that we can try gamma of t comma 1 by gamma of t. Hello. Okay. So
Ma'am,
now
audible.
will it create any problem? Hello. What?
Yes, audible.
Okay. So now if suppose so this x and y, if this suppose this is our x and this is our y, and the problem will there will be a problem if gamma of t equal to 0. So how we can tackle this issue? So as you said, if we take the path ty plus 1 minus t into x, right? That means that will be a straight line. Suppose that gamma of t equal to 0 at some points in the straight line. In that case, you can choose such that this gamma of t does not take the value 0. So such gamma of t we can surely construct. So we can use that gamma of t as a path between 1 by x, x comma 1 by x and 1 by y. So if so we can try this p of t is equal to gamma of t comma 1 by gamma of t. So in that case, if gamma of t equal to 0 at some point t, that will create a problem. So in order to avoid that problem, we will choose a gamma of t such that we will choose a path gamma from x to y such that it does not touches 0. Okay. So the second one will be path connected, hence it will be connected. Okay.
Ma'am?
Ah.
Ma'am, we can't solve the first situation through this concept.
In first situation, what is the problem? So in first situation, that this was the first graph. Okay. So what will happen? So you are taking 2 points, x comma y belongs to real numbers, and you have to construct a path between 1 by x and 1 by y. So suppose we take 2 real numbers. Suppose we take 2 real numbers. So one real number is -1 and other real number is 1. So can you construct a path gamma such that it does not take, so a gamma should be a path connect in R. The path should lie in R. So here x and y belongs, in the previous case, x and y belongs to C. So we were in 2 dimension. Here we are in 1 dimension. So if we construct a path in -1 to 1, that path should be like this only. So this path will assume the value gamma of t, this path will assume the value 0 at some point. So we cannot get a path connecting say -1 and 1 without assuming the value 0.
Okay, ma'am. Got it.
That was a good question. So now we can move on to the next question. Let A be an element of M4R with characteristic polynomial t to the power 4 minus t. What is the characteristic polynomial of A square? So we have to find the characteristic polynomial of a square. So what are the characteristic roots of the polynomial t to the power 4 minus t? What will be the characteristic roots of this polynomial?
0, 1, omega 1.
0, 1, and 1.
0, 1, omega. Okay. If we treat this matrix as a complex matrix, this is a real matrix. This M4R is a real matrix. But we can treat this matrix as a complex matrix and we can find the characteristic polynomial. It will be same only. So if we treat this as a complex matrix, we will get 4 eigenvalues: 0, omega, omega square, and 1. That is 0 and together with cube root of unity. Okay. Now, if 0, omega, omega square, 1 are the eigenvalues of A, then what will be the eigenvalues of A square?
Same.
Same, it will be same. That is 0 eigenvalues. So if eigenvalues of A is lambda 1, lambda 2, etc., lambda n, eigenvalues of A square will be lambda 1 square, lambda 2 square, etc., lambda n square. So here eigenvalues of A square will be 0, omega square, omega raised to 4. Omega raised to 4 is again omega, and 1. So the characteristic roots are same. So what will be the characteristic polynomial of A square?
This also the same.
Yeah, it will be same. That will be t raised to 4 minus t. Okay. So now we can move on to the next question. Let T be the linear transformation from the real vector space R of x to itself. R of x means polynomials with real coefficients. Polynomials in x with real coefficients. Given by T of f equal to f dash, where f dash is the derivative of f. Consider the following statements about T. That is, T is nilpotent and the only eigenvalue of T is 0. And we have to find out which of the statements are true or false. Okay. So before that, what is a nilpotent operator? When we say that an operator is nilpotent or a linear transformation is nilpotent.
If a to the power k is 0, k
for some k belongs to n, right?
K is greater than 1.
Yeah, correct. So can you try to, what are the immediate elements coming to your mind when we say polynomials?
Basis
We can consider, tell me. Hello?
basis element, basis of Rx.
Yeah, that is 1x, x square, x cube, like that. So now, can you find the, so nilpotent means we have to check whether this map is nilpotent. So we have to find t square, t cube. We have to get a structure of that. So can you say the mappings? So if we take the base elements 1x, x square, x cube, etc., t will take 1 to 0. T of 1 will be equal to 0. T of x will be equal to 1. And t square of x will be 0. Again, x, if we take x square, t of x will be 2x, t square of x will be 2, t cube of x square will be 0. Likewise, it will move on. So, can this map be nilpotent?
K will not be fixed, no, man.
What?
In each case means for nilpotency, we need a fixed k in natural numbers, so the t power k is 0. But if we fix some k, then we can choose x k plus s power k plus 1. That will not be 0.
Yeah, very good. So this map cannot be nilpotent. Now, can you talk about the eigenvalues of this linear transformation T? When we say that it has an eigenvalue, that is TF equal to, tell me.
Ma'am, but we take least such a k, na? So here we can take least such k. So we get nilpotent matrix.
Nilpotent, but this 1x, x square, x cube, it is not ending at some point.
But we
So
cannot
if
get
you
any list positive
What?
real number. No? We cannot get any list k. Is it?
So, 1 minute. So she's trying, I think she's trying to say, suppose t to the power k equal to 0 for some k. That means t to the power k of every f should be equal to 0. So in particular, if we choose f of x equal to x to the power k plus 1. So what will be t of x? T of f. T of f will be f dash, which is equal to k plus 1 into x raised to k. And f double dash will be, so the mapping will be x to the power k plus 1. And t will take this to x to the power k plus 1 into x to the power k. And t square will take this to x plus 1 into k into x to the power k minus 1. And t cube will map this to, again this k minus 1 will come outside, x to the power k minus 2. Likewise, t to the power k will be some k plus 1 factorial into x. So this is not equal to 0.
Okay, ma'am, I got it.
So now, so this map cannot be nilpotent. Now, can we talk about the eigenvalues? So what is the definition of an eigenvalue? If we get a non-zero polynomial f such that tf equal to lambda f, that means f dash equal to lambda f. So start with a non-zero polynomial f such that f equal to a0 plus a1x plus a2x square plus etc. plus an x raised to n, where that leading coefficient is not equal to 0. So now, if we equate tf equal to lambda f, what is tf? F dash. F dash is a1 plus 2a2x plus etc. plus nan x to the power n minus 1. This we should equate to lambda of f. That is lambda a0 plus lambda a1x plus etc. plus lambda an minus 1 x raised to n minus 1 plus lambda an x raised to n. So we have to find which all lambdas will be eigenvalues. So can you compare the coefficients and then can you infer something?
Lambda n will be 0. Since n is not
Exactly.
0, so lambda 0.
Lambda equal to 0. So lambda equal to 0 is the only possible eigenvalue. And what will be the corresponding eigenfunctions? Eigenfunctions mean tf should be equal to 0. That is f dash equal to 0. F dash equal to 0 means
F is constant.
f is constant. So all the non-zero constant functions will be the eigenfunctions corresponding to lambda equal to 0. Okay. So this operator t is not a nilpotent operator, but it is the only possible eigenvalue is 0. But suppose instead of r of s, if we take only this much elements, say some 1, suppose this suppose our family is the span of these elements, if fixed elements. So in that case, as someone said, this will become a nilpotent matrix. But here it is not stopping at point. So if it is some till x to the, say some x to the power 5 or x to the power 3. So the map will be 1 will be mapped to 0, x will be mapped to 1, 1 will be mapped to 0, x square mapped will be mapped to 2x, this will be mapped to 2, this will be mapped to 0, this will be mapped to 3x square, this will be mapped to 6x, it will be mapped to 6, this will be 0. So this is t square, this is t cube, and this is t raised to 4. So in this case, t to the power 4 will be equal to 0. That means this will become a nilpotent matrix. Why? It is stopping at some point. But if it go on if we have all the basis elements, then if it is not stopping, then it will not be a nilpotent operator. So that should not be confused. Okay. So we can move to the next question. What is the cardinality of the set of theta belongs to 0 to 2 pi such that the linear map R2 to R2 given by the matrix cos theta minus sin theta cos theta has an eigenvector in R2. So this is a linear map. So this is a matrix corresponding to a linear map. So can you guess the geometry of this linear map?
This is a rotation, ma'am. So for
Yes.
theta equal to 0 and pi, it will have a real eigenvalue. So option 2.
Yeah, why only theta equal to 0 and pi? Okay, you are computing the, okay, fine. If you compute the eigenvalues, then finally you will end up in e to the power I theta, which will take real values only when theta equal to 0 and theta equal to pi. Or else we can think geometrically, that is here what is happening. Here if you see 1 0 will be mapped to cos theta sin theta and 0 1 will be mapped to cos pi by 2 plus theta sin pi by 2 plus theta. So the map is coming like this. So this is our point 1 0 and 1 0 is mapped to cos theta sin theta. That means this is the theta. So this is cos theta sin theta. And 0 1 is mapped to pi by 2 plus theta. So this is cos pi by 2 plus theta, comma sin pi by 2 plus theta. Okay. So here we are taking this 1 0, we are rotating it by theta. Here also we are rotating it by theta. So this is the matrix corresponding to rotation by theta. So when this will have an eigenvalue, means after rotation, suppose if we take a vector, suppose this is our vector v. So when we have, so suppose this is the t. So if we take, so vector v. So suppose TV equal to lambda v. What does it mean?
TV lie on the same line.
After applying the operator t, this vector should lie again in the same line. So if we give the operation theta, that means it will be rotated to some point. So it will not lie in this line. So if it is theta equal to 0, then again it will be in the same line. And if theta equal to 1, so if theta equal to 0, so this vector itself will become an, again that will come, any vector will become equal, any vector will be a eigenvector. And if theta equal to pi, in that case, that vector will come in the opposite direction. But anyway, that will lie on the line itself. That is, after applying the operator t, we should get the resultant vector also should be in, the resultant vector also should be in this line. That's why we are getting theta equal to 0 and theta equal to pi. So this is the geometrical intuition. So now move on to the next question. Let P be a prime number and let A equal 2, -1, 1, 0 viewed as a 2 by 2 matrix with integer entries. What is the smallest positive integer n such that the matrix A to the power n is congruent to the 2 by 2 identity matrix modulo P? What does it mean by saying A to the power n is congruent to the 2 by 2 identity matrix modulo P means term by term. That is, if we take in entry wise, if we compute A to the power n and consider entry wise, and that should be congruent modulo P to terms in identity matrix. Okay. So ultimately, we have to find a pattern for A to the power n. So we can try for it. So our A equal to 2 - 1, 1, 0. A square equal to, I have computed it here. That is 3 - 2, 2 - 1. A cube equal to 4 - 3, 3 - 2. So can you guess A to the power n from this pattern? You just look at the entries, each entries. So can you
Is it-
One
is
n
it
plus
m
1.
n plus 1 and then minus of n minus 1, then sorry, n plus 1 minus n and minus 1, is it?
Yes, exactly. Minus n minus 1. So this is our a power n. So a power n will be equal to n plus 1 minus n minus n minus 1. So this you can prove using induction. So now what we have to do, we have to find for which minimum, we have to find the minimum n for which this is congruent to identity matrix modulo P. That means we should get an value of n such that this is congruent to 1001. That is n plus 1 congruent to 1 mod P and n congruent to 0 mod P. Other two equations also reduced to the same equation. So ultimately, this will be congruent modulo P if and only if n is congruent to 0 mod P. So which will be the least n satisfying this condition?
P.
P. Okay. So this is the P is the answer. So can we move to the next question?
Yes, ma'am.
Ma'am, please repeat it. Can you repeat it?
Here we should get a to the power n is congruent modulo 1001 mod P. That is entry wise we have to check. That is n plus 1 should be congruent modulo. So our matrix a to the power n equal to n plus 1 minus n minus n minus 1. This should be congruent modulo 1001 mod P. That means we should get 4 equations. N plus 1 congruent modulo 1 mod P. Minus n congruent to 0 mod P. N congruent to 0 mod P. And minus n plus 1 congruent to, 1 mod P. So from this, what we are getting, if we cancel 1 on both sides, n is congruent to 0 mod P. Here also we are getting n is congruent to 0 mod P. Here also we are getting, this is minus n, but still. Here also we are ultimately getting n is congruent to 0 mod P. Here, if we cancel out 1, again minus n congruent to 0 mod P, that is n is congruent to 0 mod P. That means ultimately we are getting n is a multiple of P. So n can be P, 2P, 3P, etc. So which is the least possible value?
P.
P. Is it fine now?
Yes, ma'am.
Okay. So now we can move on to the next question. Let P be a prime number. What is the number of elements in the group Q by Z that have order exactly P? So let you just take P equal to 5. So what are the elements in Q by Z that comes to your mind immediately, which has order exactly 5?
Four.
Any
5p element of P of order P in Q by Z.
Yeah, we have assumed that for the time being, we have assumed that P equal to 5. We have to find some elements in Q by Z such that Q by Z elements will be of the form sum A by B plus A by B plus Z. In this form it will be. So, and it should have order equal to 5. That means when we add these elements 5 times, we should get 0. That is
1 by 5 plus Z. 2 by 5 plus Z.
A. Yeah. we should get it as z. So as you said, 1 by 5 plus z, 2 by 5 plus z, 3 by 5 plus z, and 4 by 5 plus z. And 5 by 5 plus z is z itself. That will be, order will be 0. So if we take t equal to 5, we are getting 4 immediate elements such that its order is equal to 5. So will there be any other elements with order equal to 5?
No, ma'am.
Why?
Because in Q by Z there are exactly 5p element of order P.
That is, suppose if we, so in general, since we started with p equal to 5, we are getting 1 by 5, 2 by 5, 3 by 5, 4 by 5, etc. So in general, if we take p, what will be the corresponding elements? 1 by p plus z, 2 by p plus z, 3 by p plus z, etc. p minus 1 p divided by z. P minus 1 divided by p plus z. So that will be the elements which comes immediately to our mind with order p. Now, if any other, we have to check any other, if there is any other possibilities. That is, if we take any a by b plus z belongs to q by z, where GCD of a b equal to 1. And if we add this element p times, and if we are getting 0, that means a by b times, p times a by b is a integer. That means AP equal to BZ. And that means B divides AP. B divides AP and GCD of AB equal to 1. Then B divide P. If B divides P, only two possibilities. Either B equal to 1 or B equal to P. If B equal to 1, the elements will be A plus Z. That is Z itself. So its order will be 0 in that case. So if b equal to 1, a by b plus z will be equal to a plus z, which is equal to z, which is 0. So that will be the 0 element. And if b equal to p, again we can apply the division algorithm for a, and again we will end up in the previous situation. So only this 1 by p, 2 by p, etc. p minus 1 p elements will have order p. So we will get p minus 1 elements. Is it clear?
Yes, ma'am.
Okay. So now it is an easy question. Consider the real polynomial f of x equal to x to the power 11 minus x to the power 7 plus x square minus 1. Which of the following sentences is correct? That is, f of x has exactly 1 positive root, f of x has exactly 2 positive root, like. So we have to find out how many positive roots are there for this real polynomial. So when we get questions like this, we can try to simplify this. So f of x equal to x to the power 11 minus x to the power 7. So we can take x to the power 7 outside, and we can split into 2, x square minus 1 into x square plus 1 plus x square minus 1. So we can take x square minus 1 outside. Then what we will get? X raised to 7 into x square plus 1 plus 1. So we have two terms. So for the second term, if x is strictly positive, that right hand term will also be strictly positive. So that will not contribute any positive 0. So what is the only positive root of this polynomial?
1.
1. So
1.
so x equal to 1 is the only possible positive root. So f of x has exactly 1 positive root. Okay.
Please repeat the last step.
Yeah. Here we are factorizing into two pieces. That is x square minus 1 into we are getting x raised to 7 in x square plus 1 plus x square minus 1. I guess this was the terms, right? Yeah. So we can take x square minus 1 outside. So x power 7 into x square plus 1 plus 1. So this you can factorize it to x minus 1 into x plus 1. And again, this will be, this we don't know, this is a big polynomial. Okay, so this is a positive root. This is not a positive root. Now we have to check whether there is any positive root. So if x is a positive number, then this is our f of x. Suppose f is a positive number other than 1. Okay, say some x equal to, x is other than 1. So this part will not be equal to 0. This part will not be equal to 0. And if we check this part, whatever be the positive real number we taking, this part will be strictly bigger than 1. So this will never become equal to 0. So f of x cannot be equal to 0 in that case. If f of x has to be equal to 0, either this has to be 0, or this has to be 0, or this has to be 0. And if x not equal to 1, this is not 0, this is not 0. So only possibility is this should be equal to 0. But for any positive number, this will be strictly bigger than 1. So this cannot be equal to 0.
Yes, ma'am. Got it.
Okay. So f of x has exactly one positive root. So now we can move on to the next question. Let m be the number of positive integers n such that 1 less than or equal to n less than or equal to 2022 and such that n has an odd number of positive integer divisors. So what we are doing, we will take one element n, we will check how many divisors it will have. So if it has odd number of positive divisors, then that will be counted. Okay, so can you tell some integers or some natural numbers with odd number of divisors?
Four, 9, 16.
Huh? Which one?
4, 9, 16.
4, 9, 6. So if we take some 5, so what will be the divisors of 5? 1 and 5. So it has 2 divisors. So it is not odd number. If we take 6, that is the divisors will be 1, 2, 3 and 6. So it will have 4 divisors. So it is not odd number. So that is not possible. So the only possibility is the same thing should repeat at one point. So it will be counted as 1. That odd number we will get. So if we take the perfect squares, that is 1, 4, 9, 16, etc., that will have odd number of divisors. What are the divisors of 4? 1, 2, 4. It has odd number of divisors. 9, 1, 3, 9. So it has odd number of divisors. And exactly 3. And if we take 16, 1, 4, 16. 25, if it is 25, 1, 5, 25. So in all these cases, we will get odd number of divisors. So the question reduces to, that is if we write n equal to p1 power n1, p2 power n2, etc., pk power nk, the number of divisors for n will be 1 plus n1 into 1 plus n2, etc., 1 plus nk. And this number of divisors is odd. That means each term has to be odd. If each term is odd, then n1, n2, etc., nk has to be even. That means p1 square term, that square term should be there for each prime number. So that means n is a perfect square. So the question reduces to how many perfect squares are there in between 1 and 2022. So what is your answer?
44.
44, correct. So this is how we decode a question. So next question is, let S be the set of non-negative continuous functions f on closed interval 0, 1, satisfying integral 0 to 1 sine square x f of x dx equal to integral 0 to 1 sine x cos x f of x dx equal to, tell me.
Please repeat the last question, last part.
Oh, I'm sorry. Which part?
Last part, like, how are you concluding that part?
Yeah. Here you are getting n has odd number. This first step is fine, right? This is fine.
Yes,
Is it
yes.
fine? Okay. So now we have assumed n has odd number of positive divisors. So that means that product is an odd number. That means each term has to be odd. Why? If one of them is even, then the total product will become an even number. So each term has to be an odd number. That is 1 plus n1 should be odd number. 1 plus n2 should be odd number. 1 plus nk should be odd number. 1 plus n1 is an odd number means n1 is an even number. 1 plus n2 is an odd number means n2 is an even number. Likewise, nk is an even number. So our n will be of the form n equal to p1 power n1, p2 power n2, p2 power n2, etc. pk power nk. And we are getting this n1 is n1 is even. So n1 equal to say some 2 times m1. n2 equal to 2 times m2. And nk equal to say some 2 times mk. So this will become equal to p1 2 to the power mk, p2 to m1 2 to the power m2, etc. pk 2 to the power mk. So this is p1 square all power m1, or else we can write it as p1 power m1 whole square, p2 power m2 whole square, etc. pk power mk whole square. That means p1 power m1 into p2 power m2, etc. pk power mk whole square. So that means n is a perfect square. Is it clear?
Yes, ma'am.
Should I repeat?
No, it's okay now.
Okay. So, okay. So we were in the other question. So, okay. So this f is a non-negative continuous function. That is, f is greater than or equal to 0. And we have 3 equalities, so each of them equal to 1. Then s is. So we have to find how many possibilities are there for such continuous functions. So what are the identities coming to your mind related to sine square, cos square, sin x, cos x, all those things?
Sin square plus cos square equal to 1. So we can add first and third.
Yeah. So we know that sin square plus cos square equal to 1. So from that, what we can conclude? Integral 0 to 1 f of x dx will be equal to
2.
2. Now, any other equations coming to your mind? Sin theta, cos theta.
Equal to sin 2 theta equal to 2 sin theta cos theta.
2 sin theta, cos theta. So that also we can use. So we can, many identities are coming to your mind. That is, we have integral sin square x into f of x equal to 0 to 1. Integral 0 to 1 cos square x f of x equal to 1. From this, we are getting integral 0 to 1 f of x dx equal to 2, because sin square theta plus cos square theta equal to 1. So this is a one valid conclusion. Other thing you said is sin x cos x equal to sin 2x divided by 2. So the other equation was integral 0 to 1 sin x cos x dx equal to half times integral 0 to 1 f of x was also there. Sin 2x f of x equal to 1. That means integral 0 to 1 sin 2x f of x equal to 2. So we have 2. So from this, is it possible to conclude anything? And we know that f is a positive function. That is, f is greater than or equal to 0. Hello, did someone say something?
Yes, ma'am. Actually, I wanted to say that can we take the integral from 0 to 1 and sin x minus cos x whole square dx?
Yeah, that also you can consider.
And it will become 0, but it is not possible because the square function is always positive.
Yeah, that is also a correct argument. So this is also possible. So you are saying this one. You are taking sin x minus cos x whole square f of x dx equal to, you are expanding it, you will get it as 0. So we will get f, since f greater than or equal to 0 implies we will get, this is a positive function. So this has to be identically equal to 0. That means sin x equal to cos x only at most some finite points. In all other points, f of x has to be identically equal to 0. And by continuity of f, we should get f is identically equal to 0. But if f is identically equal to 0, then what will be the value of integral 0 to 1 sin square x f of x dx?
0.
0. So this condition will not be satisfied. So you can think in this way. This is one way, and this is another way. That is, we are getting a positive, and this sin 2x will also be positive in 0 to 1, because till 0 to pi sin is positive. So this 1 is coming somewhere here. So sin 2x is always positive in this interval, and this will be strictly less than f of x. So this integral value should be strictly lesser. This cannot be equal actually. So likewise also you can contradict. So whatever identities comes to your mind, try to arrive some conclusions from this identity, from that immediate identities, and then put it in the what conclusion you will get, and then you will compare with the other possibilities also. Okay. So is it okay now?
Yes, ma'am.
Okay. So the answer is there will not be any such function. The S will be an empty set. So now we can move on to the next question. F of x is equal to 1 minus sin x for x belongs to R. Define an equal to nth root of f of 1 by n, f of 2 by n, etc. f of n by n. So the question is related to convergence of an. So what is our an? An is nth root of f of 1 by n, f of 2 by n, etc. f of n by n. So an power n equal to, for simplicity, that will be equal to f of 1 by n, f of 2 by n, etc. f of n by n. And n log n, if we take logarithm on both sides, n log n, n log an will be equal to log f of 1 by n plus log f of 2 by n plus etc. plus log f of n by n. So log an will be equal to 1 by n into log f of 1 by n plus log f of 2 by n plus etc. plus log f of n by n. So now can you connect this limit to some Riemann integral? When
Yes.
we get something 1 by n into something plus plus plus. So can you connect this to a Riemann integral?
This will be integral 0 to 1 log f of r dx.
Yes, log f of x dx. Why? Because
Log is continuous monotone.
Yeah. Suppose if f is a continuous function on closed interval 0, 1, then this is our 0, this is our 1. So this is 1 by n, this is 2 by n, etc. This is n minus 1 divided by n. This is n by n. And suppose our function f should be f, let it be something like this. And consider, so this is the function value corresponding to 1 by n. This is the function value corresponding to 2 by n. Likewise, this is the function value corresponding to 3 by n. This is the function value corresponding to n minus 1 divided by n. So This integral can be, so find out the area, find this area. So this area will be 1 by n into f of 1 by n. Now this area, now find out this area. This area will be, again, the length of the interval is 1 by n. So this function value is f of 2 by n. Now this area, find out this area. So this area will be, again, the length of the interval is 1 by n. Function value is f of 3 by n. F of 3 by n plus etc. plus this is n minus 1. This area we will figure it out. That is f of n minus 1 divided by n plus this area we will figure out. So this area will be equal to f of n by n. Okay. So this, where will this limit will converge to? This is actually Riemann sum. So when 1 by n converges to 0, this, as n tends to infinity, that means we are refining these partitions very small. So this will be converging to, as n tends to infinity, this will be converging to the area under this curve, which is equal to integral 0 to 1 f of x dx. So whenever we get we get a structure like this, that is 1 by n into f of 1 by n plus f of 2 by n into something like that. That is ultimately 1 by n into summation f of k by n, where k varies from 1 to n. This limit will converge to integral 0 to 1 f of x dx when f is Riemann integrable. Okay. So here the function is 1 by n into, for avoiding confusion, we can put g of k by n equal to log of f of k by n. So g of x will be equal to log of f of x. So limit n tends to infinity, log a n will be equal to integral 0 to 1 g of x dx, which will be equal to integral 0 to 1 log f of x dx, which is equal to integral 0 to 1 log 1 minus sin x dx, which will be a finite value. Why? This log will be a continuous function. It will create a problem only if 1 equal to sin x. But 1 equal to sin x when x equal to pi by 2. But pi by 2 is beyond 1. We are integrating only from 0 to 1. So this inner part will never become 0 in this interval. So this log will be continuous function. So this continuous function, we are integrating a continuous function on a bounded interval. So that value will be some finite limit. Some finite real number. So what we can say, log an converges to L. So if we take exponential on both sides, we will get a to the power n will converge to e to the power n. Because if we have an converges to a and f is a continuous function, f of an will converge to f of a. So exponential function is a continuous function. So log an converges to L implies exponential of log an will converge to exponential of L. That is, an will converge to e to the power L. So the options is an converges to e to the power L, and it cannot be equal to 0. So what will be the option?
Third option.
Third option. So is it okay, this question?
Excuse me, ma'am.
Huh.
Ma'am, please can you repeat from the Riemann integral?
Okay. So is it okay for you till here?
Yes, ma'am.
Okay. So here, if f is the continuous function, and if we get, if f is a continuous function, we have, say, f is continuous on closed interval 0, 1. In this case, 1 by n summation k equal to 1 to n, f of k by n should converge to integral 0 to 1 f of x dx. Is it clear to you? This part?
Yes, ma'am.
Now our terms was coming like this. Log an equal to 1 by n into something plus some function of k by n. It is coming. So we should integrate, instead of integrating f of x, here we should integrate integral 0 to 1. What we should integrate? So our log an equal to 1 by n into log f of 1 by n plus log f of 2 by n plus etc. plus log f of n by n. Okay. So 1 by n into this term. You consider only this term. Where will this converge to? So this you can call it as g of 1 by n. This you can call it as g of 2 by n. This you can call it as g of n by n. So this will converge to here 1 by n into f of 1 by n plus f of 2 by n plus etc. plus f of n by n. This is converging to integral 0 to 1 f of x dx. So here where it will converge to? Hello?
Integral 0 1 gx dx.
Integral 0 to 1 g of x dx. So is it clear to you now? This step, is it clear to you? Somebody asked me that.
Yes, ma'am.
Is this step clear to you? Till here, is it okay?
Yes, ma'am.
Now what is g of x? We know g of 1 by n or g of k by n is equal to log f of k by n. So what is the obvious choice of g of x? When here it is k by n, here it is k by n. When it is x here, what will be the obvious choice of g of x? What will be our g of x?
Log of f of x.
Log of f of x. So this is equal to integral 0 to 1 log of f of x. And in the question, they have given that f of x equal to 1 minus sin x. So log f of x, which is equal to log 1 minus sin x. Then we are just integrating a continuous function on a bounded interval. Is it okay now?
Yes, ma'am.
Okay. So next question is, which of the following is true for every function u from R to R, which is continuously differentiable on R and satisfy u of y is greater than or equal to u of x plus u dash of x into y minus x for all x, y belongs to R. And we have to check what is u dash. U dash is non-negative, u dash is not decreasing, u dash is non-increasing. Likewise. So what are the immediate functions coming to your mind satisfying this condition? U of y greater than or equal to u of x plus u dash of x into y minus x. Can you give one example?
Identity function.
Identity function. So if we take u of x equal to x, this will work. Now, any other similar functions? That was a good start. Start with identity function. And some other examples coming to your mind?
X square we can take, I think.
X square, that is also a very good example. Then, can we try minus x? u of x equal to minus x? Will it satisfy this function condition? Yes, that also will satisfy. So we are getting some examples for some functions satisfying this condition, and we are going to study the study about u dash. So if we take u of x equal to minus x, u dash of x will be equal to minus 1. So can we discard any options?
Ma'am, non-negative one, I think.
Yeah, so u dash is non-negative, that we can discard. Any other options can we discard?
Second option.
Second option we can discuss. U attains its minimum at some x belongs to R. That also we can discard. So what remains is about the study of u dash. We have to figure it out whether u dash is non-decreasing or u dash is non-increasing. So for that, start with x less than y. And we have u of y minus u of x is greater than or equal to u dash of x into y minus x. And if x is strictly less than y, then y minus x will be positive. So even if we divide the whole inequality with y minus x, the inequality remains same, since we are dividing it with a positive quantity. So we will get u dash of x will be less than or equal to u of y minus u of x divided by y minus x. Okay. Now, this is true for all xy. So, in particular, we can swap x and y. So, from that, we will get u of x minus u of y is greater than or equal to u dash of y into x minus y. But x minus y is negative. So, now we are going to divide it with a negative term. So, the inequality will be reversed. So, u of x minus u of y divided by x minus y will be less than or equal to u dash of y. So now if we combine 1 and 2, we will get u dash of x will be less than or equal to u dash of y. So option C is true. Now about, is it okay now? Hello?
Yes, ma'am.
Now, can you discard the fourth option? So now we got an idea that u dash is non-decreasing. So can you discard the other option with any of the familiar examples? We know u of x equal to x square. What will be u dash of x?
2x. It is
2x, which is strictly increasing. So non-increasing option also we can discard. So we will get u dash is non-decreasing. That is the correct option. Shall we move to next question? Any
Yes,
doubts? Okay. Now, the value of limit n tends to infinity, integral 0 to 1, n e to the power x divided by 1 plus n square x square dx. So, do you know any familiar result to exchange the limit and integration? Or else if we, tell me.
Uniform continuity, right?
Yeah, if we have uniform convergence.
Convergence, yeah.
So here, if we take fn of x equal to n e to the power x divided by 1 plus n square x square, what will be the limit of this function? That is, what I am telling is, take, fn of x equal to, what was the function? Fn of x equal to n e to the power x. N e to the power x divided by 1 plus n square x square. What will be fn of 0? Tell me fn of 0.
Zero.
Fn of 0. E to the power 0 is
n
n.
Now, what is fn of x? Fn, so this is going to infinity. Now, what about fn of x? Fn of x is equal to n. So we are fixing an x. So, or in order to avoid the confusion, call it as some a, some constant a, where a belongs to 0, 1. We are talking about the integral in 0, 1, right? Oh, yeah. So n e to the power a divided by. So where it will converge to? As n tends to infinity.
It's converging to 0, I guess.
0. You can use the L'Hopital's rule and all. So we are getting the limit here. Each function is continuous. So if it is uniform convergence, the limit should also be continuous. But here the limit is not continuous. So this uniform convergence we cannot use. So any other theorems? Do you
Ma'am,
know?
actually, I personally prefer like something called sandwich theorem. Like you can use some inequality of ex or 1 plus n square to make some inequality of the integral, and then you can conclude both the side limits are tending towards the same value.
But here, the thing is here each term is we have to find limit of integral 0 to 1 n e to the power x divided by 1 plus n square x square dx. But here, if we are able to interchange the limit and integration, it should come like this. This will be equal to n e to the power x divided by 1 plus n square x square. That means, but here the limit value will be equal to 0, except at value 0. So again, that will not matter. So this will become identically equal to 0. So the limit of this is becoming 0. But in the options, if you look at the option, 0 is not there. So we cannot use any uniform convergence theorem or monotone convergence theorem or dominated convergence theorem. We cannot use. So what else we can use?
No, ma'am. Like I was saying, if you use e raised to x is greater than equals to 1 plus x and less than equals to 1 plus x square in the interval 0 to 1, and you apply this inequality in the integral, you will get the answer, I think.
Yeah, 1 minute. Can you just repeat it? You are
like e raised to x. Ma'am, only write e raised to x. Since e raised to x is less than equals to yeah, it is greater than equals to 1 plus x. Like e raised to x is greater than e raised to x is greater than equals to 1 plus x, right? Yeah, yes, ma'am. This thing. And then apply both sides.
Then what happens?
Yeah, then then we can compute in this integral, and then for other inequality, we can use e raised to x is less than or equals to 1 plus x square.
E to the power x is less than or equal to 1 plus x plus x square.
In the interval 0 to 1.
Okay, in 0 to 1.
Yeah.
Oh, okay. Okay, you can use that also.
And like
and
this,
then you tell me.
In integrals we will get are very easy to compute with compared to the given integral, right?
Okay. So you can compute this integral and you can compute this integral, and then you are trying to use that sandwich theorem or something like that.
Yes, ma'am.
Okay. That is possible. Or else we can use integration by parts. So integration by parts is integral 0 to 1 n e to the power x divided by 1 plus n square x square dx equal to e to the power x into tan inverse nx 0 to 1 and integral 0 to 1 e to the power x tan inverse nx. So this will be, first term will become, after giving the limits, e into tan inverse n minus integral 0 to 1 e to the power x into tan inverse nx dx. And can we use monotone convergence theorem or dominated convergence theorem for getting second integral, the actual value of the second integral? Do you know monotone convergence theorem or dominated convergence theorem?
Ma'am, if you write little, it will be helpful. Actually,
Okay. So monotone convergence theorem says if we have a sequence of positive functions such that fn is increasing and f wise, then integral 0 to 1 fn of x will converge to integral 0 to 1 f of x dx. So this is monotone convergence theorem. So here we can interchange the limit and integration. Dominated convergence theorem says that if we can find a g such that mod fn less than or equal to g and this g is integrable, then in that, and we have fn of x converge to f of x point wise, then also we can interchange the limit and integration. So these are the two important theorems we can use to interchange the limit and integration: monotone convergence theorem and dominated convergence theorem. So
in the monotone convergence theorem, this convergence is pointwise, right?
Yeah.
Okay. Thank you.
So, and then as you said, you can use this fn converges to f uniformly, then integral fn will converge to integral f. This also we can use. So by using monotone convergence and monotone convergence theorem or dominated convergence theorem, whatever, here we can say fn of x equal to the second integral e to the power x tan inverse nx. Oh, sorry, it is tan inverse nx, not tan inverse x. So e to the power x tan inverse nx, we can bound it by e to the power by pi by 2, and it is on closed interval 0, 1. So this is integrable on closed interval 0, 1. So here we can exchange the limit and integration. So tan inverse nx will converge to, if x belongs to open interval 0, 1, tan inverse nx will converge to pi by 2. E to the power x tan inverse nx will converge to e to the power x into pi by 2. And by using dominated convergence theorem, integral 0 to 1 e to the power x tan inverse nx will converge to integral 0 to 1 e to the power x into pi by 2, which is equal to pi by 2 into e minus 1. Now we can substitute this in the previous equation, where the equation where we get from what we get from integration by parts. So integral 0 to 1 n e to the power x divided by 1 plus n square x square dx equal to e into tan inverse n minus integral 0 to 1 this integral. Just now we got it as pi by 2 into e minus 1. So if we substitute everything, tan inverse n will go to pi by 2 when n tends to infinity. So when n tends to infinity, we will get this limit as pi by 2. Okay. So I hope the question is clear to you. Should I explain more? Should I repeat the previous question? Is it clear to you?
Yes, ma'am, it is clear.
Okay. So now this is an easy question. What is the number of real solutions of the equation e to the power sin x equal to pi? What is the maximum value of sin x?
1, ma'am.
1. So what is so e to the power sin x, what will be the maximum value of e to the power sin x?
E.
E. So which is bigger, e or pi? Can it become equal to pi?
No, ma'am, never.
Okay. So so this equation do not have any real solution. Okay. So now we will move on to true or false questions. So first question is R2 minus Q2 is connected but not path connected. Path connected means if we take any arbitrary points, we should be able to find a path in the set. Okay. So what is your opinion? R2 minus Q2, will it be path connected? So
I think yes, ma'am.
yeah, tell me.
I don't know the proof actually, but there was theorem that if A is countable, then R raised to n minus A is actually path connected.
Yeah, correct. The theorem is correct, but what is the idea of the proof? Here from R2, as you said, we are removing only countably many points. So if we take 2 points, so this is our R2. Suppose we take 2 points X and Y. Okay, so this is a path. This is a path. This is a path. This is a path. Likewise, what will be the cardinality of the possible paths from X to Y?
Infinite.
Infinite, ma'am.
Infinite means what infinity? Countable infinity or uncountable infinity?
Countable infinite.
Only countable. Suppose if we vary this, say this angle is theta, we can vary this theta from say some 0 to pi by 3. Then itself we will get uncountably many paths, right?
Yes, ma'am, it is. Yes.
Okay. So from X to Y, if we take any 2 points, we will get uncountably many paths. And from R2, we are subtracting only a countable set. So we have uncountably many points and only some countable, maybe this countably many points can come in some path. But still, we have uncountably many paths, which is completely lies in this R2 minus Q2. So that means it will be path connected always. Should I repeat it?
Yes,
Or
ma'am.
else you can think in this way. If we take some X, here if you take some Y, you have many, you have very bad drawing. Okay. So you can draw. Okay. So uncountably many lines you can draw to passing through X. And we have only countably many points we are avoiding. So say that one point lies here, another point lies here, another point lies here. But still we have more lines here. And in a similar way, here we will have uncountably many lines in which these Q2 elements will not be there. Here also we will have uncountably many elements where these Q2 elements are not there. So suppose this is one such line and this is one such line. You can just connect it. So this can be the path from X to Y. So you can think in this way also. So anyway, if you subtract or if you remove any countable number of sets, any countable number of elements from R2, still it will be path connected. So is it clear to you? Hello?
Yes, ma'am.
Okay. So the next question is, okay, if X is a connected metric space and F is a subring of C of XR, that is F field, then every element of C of XR that belongs to F is a constant function. So first of all, we have a connected metric space and each element is a continuous function. So what all the result you know if we have a continuous function and if we have a connected set?
Continuous image of a connected set is connected.
Connected. Very good. So that is one result that coming to your mind. And here we have a subring of continuous function, and it is not only a subring, it is a field. Okay. Now we have to show that every element of that field, every element that belongs to F is a constant function. So first of all, does constant functions belongs to this subring? 0 will be there, 1 will be there. If we take any element, say some 2, what will be its inverse 1 by 2? That will also be in this field. So all the constant functions will be contained in F. Now we have to show that F is contained in this constant, F is contained in the family of constant functions. So you can start with a function in capital F and you have to show that it is a constant function. So we know, as you said, x is connected, f of x is connected. And if we take f is not equal to 0, then f is invertible. Why? F is coming from a field. So every non-zero element is invertible. If f is invertible and f of x is connected, then either f will be strictly positive or f will be strictly negative. Why?
Ma'am, intermediate weather property, right?
Yeah, correct. That is, if f, suppose if f assumes 1 and f assumes -1, then f should assume 0 also. But f is invertible. So it cannot take the value 0. Here invertible means if g is said to be inverse of f, if we have fg equal to 1, that is f of x into g of x should be equal to 1. Okay. So either it should be completely either f should be completely positive or f should be completely negative. So without loss of generality, assume that f is strictly positive. And if possible, suppose f is non-constant, and we know that if f is non-constant, f of x will contain an interval. That is, if f is non-constant, it will assume two values, say some z1 and z2. Then this f of x is a connected set in R. So if z1 and z2 are there, then the whole interval z1, z2 will be there. Okay, so if f is any non-constant function, f of x will contain an interval. So in that we can find a rational number. So now somehow we have to reach to a function which belongs to this family f, and we have to make some contradiction. So which function comes to your field? By some, if we do some rearrangements for this f of t, or from this f of t equal to alpha by beta, what function g you can construct such that g should be an element of this field, but somehow we have to contradict, like g is not invertible or something like that. That is, g of t equal to 0 at some points, like that. So what g you can use? What is the easiest polynomial coming to your mind? Tell me.
Ma'am, like, is it, can we take, ma'am, g as constant function also?
If g is constant, then we are starting with a non-constant function.
Okay.
Ma'am,
Ah,
start with g as ft minus alpha by beta.
Yeah, we can start like this. That is, if g equal to, that I have written in a different form. Anyway, whatever you said is corrected. If g equal to, yeah, your intuition is correct. That is only I have written here. G equal to beta f minus alpha. Now, g belongs to, will g belongs to f? Will g belongs to our field?
Yes, ma'am.
Why?
Because of the properties of the field, right? Because
Yeah.
of like
F belongs to field. So f plus f belongs to field, and this b is some positive integer. So beta f will belongs to field, and 1 belongs to field. 1 plus 1 belongs to field. Like alpha. Alpha is an integer. So alpha belongs to this field. And again, it is a subring. So difference of two elements will belongs to this field f. So this g will belongs to f. Now, but g of t, what will be g of t? G of t equal to 0. In that way only we have constructed the function g. If g of t equal to 0, then what does it mean? G is not invertible, but g belongs to f. So g has to be identically equal to 0. If g is identically equal to 0, then f has to be identically equal to alpha by beta. Which implies f is a constant function, which is a contradiction. So the only possible elements in this field is constant functions. Is it clear?
Yes, ma'am. It is clear.
Hello.
Yes,
Okay.
ma'am.
So now we can move to next question. For a nilpotent matrix, A belong. When we say that a matrix is nilpotent,
Ma'am, if there exists some integer k such that a raised to k equals to 0 matrix.
yeah. So this A is a nilpotent matrix, and we are defining exponential of A equal to identity plus A by 1 factorial plus A square by 2 factorial plus etc. And if A is a nilpotent matrix such that exponential of A equal to identity matrix, then we have to show that, then what is the question? Then A is the zero matrix. So this is the question. So we can just try. Okay. So let M be the positive integer such that A to the power M equal to 0. So if A to the power M equal to 0, then all the remaining terms will be equal to 0. So e to the, and we know exponential of A equal to, that form will be reducing to till A to the power M minus 1, which is equal to identity by our assumption. Okay. So now if M equal to 1, then A is identically equal to 0. M equal to 1 means A to the power 1 equal to 0. That means A equal to 0. But if M is strictly bigger than 1, then A satisfies the equation x plus x square by 2 factorial plus etc. plus x raised to m minus 1 divided by m minus 1 factorial. Okay, so x satisfies a polynomial of degree m minus 1. So now what will be the minimal polynomial of this nilpotent matrix A? We have choose m such that m is the least positive integer such that A to the power m equal to 0. So what is the minimal polynomial of A?
X equal to 0. Means x will be the minimal polynomial.
No. From here, here we have A to the power m equal to 0. That is the nilpotent matrix. So from that, what?
X will be the minimal
Hello?
polynomial.
Yeah, we have to reach there. So what I tried to say is, if we have a nilpotent matrix in general and if m is the least positive integer, we can say x to the power m equal to x to the power m will be its minimal polynomial. But here, this satisfies a polynomial of degree m minus 1, which is not possible. And hence, this minimal polynomial has to be equal to x. That means A is identically equal to 0. Okay?
Yes, ma'am.
Okay. So now move on to the next question. Okay. So this this I will not explain completely, but we will just give a rough idea. There exists A belongs to A equal to A, B, C, D belongs to M2 of R such that A square equal to A, which is not equal to 0 and satisfies mod A plus mod B less than 1 and mod C plus mod D less than 1. So here it is computation that you can do yourself. We have given A square equal to A. So you find out A square and equate it with A. So you will get 4 equations. A square plus BC equal to A, B into A plus D equal to B, C into A plus D. Equate each term by term. And from that, you analyze this A plus D. You try to solve the 4 equations and then finally you will consider this mod A plus mod B less than 1. That all you can try. And finally, you will end up in these two inequalities. That is, in one case, we will get mod BC is less than AD. And by looking at the characteristic polynomial, we will get AD equal to BC. That we will end up in a contradiction. So there does not exist such a matrix. There is not much theory here. It's just computation. So that you can do yourself. We are almost out of time. So I'm leaving this question to you. So we will move on to next question. There exists f belongs to C is a continuous function on closed interval 0, 1, satisfying the following 2 conditions. The first condition is integral 0 to 1 f of x dx equal to 1 and limit n tends to infinity integral 0 to 1 f of x power n dx equal to 0. So the question is, does there exist a function satisfying these two conditions? Okay. So the first we have limit n tends to infinity integral 0 to 1 f of x power n dx equal to 0. Suppose this f is a positive function. Suppose this f is a positive function. Then what does it mean? Okay. So suppose this f is a positive function and we know 1 f of x power n equal to 0. And this integral is over 0, 1. That means this area is, if we take the power and the area is coming to 0. So suppose this is our f of x power n is coming like this, because smaller and smaller, and this area is become equal to 0. So if f is positive, we will get some idea of this picture. So, but here we don't know whether f is positive or negative. But we know that limit n tends to infinity integral 0 to 1 f of x power n equal to 0. So, in particular, limit 2n tends to infinity integral 0 to 1 f of x power 2n will also be equal to 0. This will be a subsequence, which is equal to integral 0 to 1 f of x whole square all power n equal to 0. So that means this is a positive function and its power is decreasing, and that integral is coming to 0. And this f is a continuous function as well. So from this, can you conclude that this mod f of x square is less than or equal to 1? Is it possible? This is 0, this is 1. Suppose if possible, mod f of x is bigger than 1 or mod f of x square. So we can take f of x is bigger than 1. That means, suppose this is our x. At some point, suppose if possible, so this is our 1. So if f of x is bigger than 1, that means in a neighborhood of that point, f of x will be bigger than 1 by continuity. So suppose this is that neighborhood. So in this neighborhood, f of x is bigger than 1. So if we take the power f of x square, it will go on increasing. Then it will go on increasing like this. It will go on. So this will this will go up to infinity. So this integral will not converge in that case. So since this integral is converging, we should have mod f of x square should be less than or equal to 1. From that, we can conclude that mod f of x is less than or equal to 1. Is it clear? How we do you get how we conclude that mod f of x is less than or equal to 1? Okay, I'll tell again. Suppose f of x equal to suppose this is our f of x. This in both sides it is equal to 1. This is 0, 1, and it is at this point x, and we are getting a neighborhood of x for which f of x is strictly bigger than 1. So if possible, f of x is bigger than 1 or f of x square, then what does it mean? There exists a neighborhood such that in that neighborhood it will be bigger than 1. So if we take the power, it will be again going on increasing. So the area will go on increasing. So this area that will go to infinity in that case. but we have integral 0 to 1 f of x square all power n is converging to 0. That means this should not happen. This happens only if f of x is bigger than 1. So if mod f of x is less than or equal to 1, at least we have a hope that this will happen. And from that, we have one more condition, that integral 0 to 1 f of x dx equal to 1. So combining these two, we will get f has to be identically equal to 1. But if f is identically equal to 1, then this condition will not be satisfied. So there does not exist any continuous function satisfying these two conditions. So we have limit n tends to infinity integral 0 to 1 f of x power n dx equal to 0. From that, we will get limit n tends to 2n tends to infinity integral 0 to 1 f of x power 2n dx equal to 0. This is just a rearrangement. And from this, we will get mod f of x is less than or equal to 1. And mod f of x less than or equal to 1 together with integral 0 to 1 f of x dx equal to 1 implies f of x has to be identically equal to 1. That you can draw a picture and then you can find it out from the picture. Then you can write the analytic explanation also. But in that case, the second condition will not be satisfied. So there does not exist such a function f. So is it clear to you?
Yeah, ma'am.
Okay. So now, next question. Let an is greater than or equal to 0 for each positive integer n. If the series summation n equal to 1 to infinity root an converges, then so does the series summation n equal to 1 to infinity an power n by 4, n raised to 1 by 4. So what is your guess? What do you feel? If summation root an converges, root an will be converging to nth term will converge to.
From here,
If
we
I
can
see
conclude that n is order of 1 by n square for large n.
what?
From here, we can conclude that n is order of 1 by n square, at least after Thum's threshold.
That how you can prove that? Okay, intuitively it is okay. But proving that, are you able to prove that statement?
Yes, ma'am. If it's not like that, if it's not like 1 by n square, so how can we tell that it should be convergent?
There can be some that 1 by n square is a special form of converging series. It is P series.
I am telling that n is order of 1 by n square, not exactly 1 by n square. Because
yeah, okay.
if it's less than, then n plus 1 by n will not converge to 0.
Yeah, but what if an is of order of 1 by n raised to some 3 by 2, something like that?
Then how can it be root n convergent? Root n will not be convergent, right?
Okay. Root n you are taking. Okay. Intuitively it is fine. Or else you can think this root an converges will imply, summation root an will converge implies nth term will converge to 0. So root an will converge to 0. That means after a finite stage, root an is less than 1. So if root an is less than 1, can you compare this an and root an? Which will be bigger?
Root n will be bigger.
Root an will be bigger. So we can say, and this an is positive. And then an by n to the power 1 by 4 and an. Which one will be bigger?
An will be bigger.
An will be bigger. So we will get an power n by 1, n raised to 1 by 4 is less than or equal to an is less than or equal to root n. So now we can use the direct comparison test. Since summation root n converges, we will get summation an by n to the power 1 by 4 will also converge. So in general, if summation an converges, then summation an square will also converge. And here there is not that much importance for this dividing by n to the power 1 by 4 and all. We are just making it further smaller. Ultimately, what we are proving is if square root summations, that is, we are proving if summation square root an converges, summation an converges. That is, if an converges, an square is convergent. Like that we are proving. So this also you can use occasionally. Now next question is, there exists a differentiable function f from R to R such that, is it okay if I take 10 more minutes, maximum 10 more minutes?
Yeah, Jiya, you can continue.
So there exists a differentiable function f from R to R such that limit x tends to infinity f of x equal to 2 and limit x tends to infinity f dash of x equal to 1. So we have two statements. Limit x tends to infinity and limit x tends to infinity f dash of x equal to 1. What does it mean? Can you just visualize such a function? Limit x tends to infinity f of x equal to 2 means when after a finite stage, the function should behave like something like 2. Right? It should go like this. And for the second condition, limit x tends to infinity, f dash of x should behave like 1. That is, f of x should behave somewhat like x. So as x tends to infinity, by this condition, we should get x behave like this, provided this is f of x equal to x. So intuitively, what do you feel? Will there be a function satisfying both the conditions?
Ma'am, actually, there's theorem also, I think.
What theorem?
Which says if limit n, the theorem is if limit n goes to infinity, fx is equals to L exists, then limit x goes to infinity, fx plus f dash x equals to L. And this fact follows from the L-Hospital rule.
Oh, okay. If you know that theorem, you can use that also. But here I was trying to give an geometric idea. Since they have specifically mentioned that limit x tends to infinity f of x equal to 2 and limit x tends to infinity f dash of x equal to 1. Okay, if you know that theorem, you can use that also. And again, what is your conclusion? What do you feel?
So, ma'am, it is false, actually.
It is false, yeah. So first you geometrically make an idea, and then you will get a compact set. Outside that compact set, this f dash of x value will lie between 1 minus epsilon and 1 plus epsilon. F of x value will lie between 2 minus epsilon and 2 plus epsilon. So then you can use what theorem comes to your mind. You can use the mean value theorem and prove it analytically. So that's it. And then we will get a contradiction. So that analytical proof, you can just go through it. We will move on to next question. Let f from closed interval 0, 1 to 0 to infinity be continuous on closed interval 0, 1 and twice differentiable in open interval 0, 1. If f double dash of x equal to 7 times f of x for all x belongs to 0, 1, then f of x is less than or equal to maximum of f of 0, f of 1 for all x belongs to closed interval 0, 1. So our function satisfy f double dash of x equal to 7 times f of x. So can you explicitly solve this differential equation? How you will solve this differential equation with constant coefficients, second order differential equations with constant coefficients? What will be the auxiliary equation?
m square minus 7 is
yes. Yeah, so m equal to plus or minus root 7. So f of x is explicitly, we can write it as a e to the power root 7x plus b e to the power minus root 7x, since the roots are distinct. Now, we have to check the critical points for f of x. So critical points, how we will evaluate critical points? Since it is a differentiable function, how we will evaluate the critical points? Will we give f dash of x equal to 0 and then find out? So give f dash of x equal to 0 and equate. So you will get x equal f dash of x equal to a root 7 e to the power root 7x equal to b root 7 e to the power minus 7x. We will get e to the power 2 root 7x equal to b by a, and x is equal to log b by a by divided by 2 root 7. And so now we get f dash of x equal to 0 at this point. Now we have to check whether it is a local maximum or local minimum. Fortunately, this is a local minimum by evaluating f double dash of x. F double dash of x is 7 times f of x. So 7 times f of you can substitute here, and then you will get it as some positive quantity. That means if this is a local minimum. So maximum will be at the end points. So f of x will be less than or equal to f of 0 or f of 1. So the maximum value will be at the end points. Okay. So that's it. And this question you can do yourself. And I'm moving to the last part. This is the last topic, but it is very important, Vandermonde matrix. This Vandermonde matrix is a matrix with the terms of the geometric progression in each row. So this is a matrix. The property of this matrix is in each row, it will be geometric series. It will be coming like a geometric series. And this you will be familiar in your 12th standard and all. You might have found out its determinant. So its determinant will be equal to x1 minus x2 into x2 minus x3 into etc. xn minus x1. So the determinant will be coming like this. And this matrix, this determinant is non-zero if and only if each of these xi's are distinct. So if each of these xi's are distinct, we can say that this V is invertible. So this is a very important matrix which will come into picture. So there will be different questions that we can solve using these kinds of matrix. So you just keep it in your mind about this matrix, and we can move to the final question, and then we will stop here. So the set f of x belongs to R of x such that f of n belongs to Z for all n belongs to Z is uncountable. So what is given? We have given R of x is the family of polynomials with real coefficients. And what is the peculiarity? If we evaluate at any integer, that f of n will also be an integer. So that is the property, which is and we have to check whether this family is uncountable. So start with a polynomial f of x equal to a0 plus a1x plus a2x square plus etc. plus an x raised to n. And we know that f of n belongs to Z for all n belongs to Z. That means f of 1 is an integer, f of 2 is an integer, f of 3 is an integer. Likewise, for any integer, f of that integer will be an integer. So what we can get? F of 1, that will be a0 plus a1 plus etc. plus an, which is equal to some integer, call it as Z0. F of 2 equal to a0 plus 2a1 plus etc. plus 2 to the power n an equal to some integer, call it as Z1. Likewise, pick n plus 1 because we have n plus 1 unknowns. So we are trying to make it as a matrix. So f of n plus 1 equal to a0 plus n plus 1 a1 plus etc. plus n plus 1 power n an equal to Zn. So what will be the corresponding matrix representation? So matrix representation will be coming like this. 1, 1, 1 into a0, a1, etc. an equal to Z0, Z1, Z2, etc. Zn. And this is a Vandermonde matrix, and all these x1, x2, x3 that are distinct. So this matrix is invertible. So a0, a1, a2, etc. an is, if we call it this matrix as V, this a0, a1, a2, etc. an will be V inverse into Z0, Z1, Z2, etc. Zn. And V inverse is adjoint of V divided by determinant of V. This determinant of V will be an integer because all the entries are integers. Adjoint will also be, each term will be an integer. So this V inverse together, the interest will be, we cannot say that it will be integer, but we can say it will be some rational numbers. So all this A0, A1, A2, etc., An will be coming from Q. So the given subcollection is a given collection is a subcollection of Q of X, and we know that Q of X is countable. So this subcollection can never become uncountable. So the answer is, the statement is false. Okay. So that's it. So if you have any questions, you can just ask. We will wind up here.
Excuse me, ma'am.
Huh.
Ma'am, can we say for the last question, in last question, in given set, f of n having a choice from z and cardinality of z is at most countably infinite. So this set could be a countable. Can we say like that?
How you conclude? We know that Z is countable, and from that, how you conclude that this family is countable?
I think that f of n belongs to z, and z is countable. That's why I say that this set could be having a countable number of choice. So I think like that.
What about if there exists an uncountable many f such that f of n will be integer? You are saying that since Z is countable, this family will be countable, but there can be, if it is countable family, there can be uncountably many f for which this f of n still belongs to Z. So that's what we are making sure that it is not possible. Finally, we will end up in Q of X. But I didn't get your argument that how you prove that. That is ultimately we are again coming back to this question, right? I'm sorry, I didn't get your question. Can you repeat it once again? You are telling Z is countable.
Ma'am, I said that here f of n is belongs to z. So
Yeah.
can we say that f of n having lf not choices?
Ma'am, actually, I want to correct her little. Fn is not belonging to Z. Fx is a member of Rx, which has the special property that whenever some integer is put it inside F, it will go to Z. It has just a special property. It is not belonging to Z.
So what do you want to ask?
Hello, ma'am.
Huh.
Actually, I hope that that girl who was telling, she's right. Actually, you can also rephrase your the last sentence like it is not Qx, it should be Zx, right? The solution that should be Zx, not in Qx.
But ZX, how you can ensure this determinant of V is an integer that need not be equal to 1. So suppose it is some, if we take first two case.
It's 1, 2, 3, 4 like n plus 1, no? So if you divide, like it should be x1 minus x2, x2 minus x3 like that only, right? So it's 1,
okay,
right?
okay. Okay.
That's why she was telling that that coefficients are coming from Z. So as the coefficients are coming from Z, let's say fix an order K. So it should be countable. Now vary the order K. It should be again countable, union of countable. So it should be countable.
Yeah.
That's why she was telling.
Yeah, correct. In that case, we have to mention that this determinant is an integer. Determinant is either +1 or -1.
Yeah.
Then it is fine. That will belongs to ZX.
I just want to say that thank you for such a wonderful session, and we get to know many new things. Thank you for this.
Thank you. Thank you. And thank you for your response also. The group was very interactive, and that made it was very energetic actually.
Sir, this is Avril Srivastav, and actually I just passed out my master's from University of Hyderabad, and now I'm planning to do PhD from Stanford Institute. So I'm looking for entrance exams and this.
Hello, ma'am. My name is Aishwarya Dhaharwar. I'm from Maharashtra. I want to thank you for this wonderful session. I enjoyed that session because you include our comments also. You are allow us to, and you you take our opinion about the question, and because of that this session is so wonderful. And thank you so much, ma'am, and thank you, Vinod sir, to arrange such kind of session. So thank you so much.
Okay, thank you, Aishwarya. Others?
I am Dharmendra. Good afternoon, sir, and good afternoon,
Yes.
ma'am. I am from Visakhapatnam, BARC Vizag Library. I am doing mathematics along with my job, and I have only BSc. This session was very enjoyable, but internet connection and some between call, I just disconnected many times. But I enjoyed this session. And last one, matrix van der Waal matrix is new for me. That is very interesting. And I want to ask some reference and textbook and your PhD experience also. Please, can you tell?
Yeah, I'm doing PhD in IIT Madras. For that, I cleared CSIR, JRF, and GATE. So at that time, I used to study the MSc prescribed text book itself, and I tried to solve the exercise questions. And like when you solve one exercise question, you ask some other questions related to that question. What if we drop one condition? What if it is not in this form exactly? Likewise, what I did was I followed the prescribed textbook itself, and then I solved the exercise questions. Solving exercise questions is very important. If we read some 10 textbook and if you are not solving any of the exercise question, that is not, I don't prefer. If we read one book, you solve all the exercise questions from each chapter and then move on to next book, so that you will get once you start doing exercises, you will get a clear idea what the theorem says, what the chapter is about, what does it mean. Likewise, you will get a clear idea when you start doing exercise questions. So that is very important. And about the textbooks you asked, for real analysis, I followed Walter Rudin. You can follow Kumaration's real analysis. Then there are problem books by American Mathematical Society in each topics. I think one book is there for sequence and series, one is for integration, and the other is for continuity, I guess. So there are 3 books in which you can see a lot of problems. So for real analysis, that you can refer. And for linear algebra, I followed Hoffman and Kunz. And more than that, I felt linear algebra by Done Right. That is also a very good book, in which you can watch the YouTube videos of this Done Right and all. So that is also good. So you can go. The thing is, you have to do the exercise questions as well. So that also you can do. Then for other subject, for algebra, I followed Frale. That also, there were a lot of exercise questions in that book. For topology, you can refer Kumaration's topology regarding metric spaces and all. We are getting a clear idea. Functional analysis, 𝕬𝕐𝕐𝕐's book is very good. Limaye's book is very good. Likewise, whatever be the book you read, you try to solve the exercise questions as well. So these were the main books I went through these days.
Thank you, ma'am.
Others?
Am I audible, sir?
Yes.
Yeah.
Hi, Jiya. Happy to see you again. It was very nice session. Most of the topics was new, but still they were understandable. They were the way you explain. It makes us very much convenient for BSc students like us, and it was very interesting because it was full of noise. Everyone was so active, and thank you so much, Chechi. Thank you so much, sir, as usual.
Thank you, Haritha.
Thank you, Haritha.
Yes,
Good afternoon,
others?
ma'am.
Yes.
I'm Shikha, a second year MSc student from Birla Institute of Technology, Mishra, Jharkhand. The session was really nice. It was very interactive. Without being annoyed, you kept on explaining twice the doubts. You cleared our doubts. Everything. Overall session was really very wonderful. Thank you, ma'am. And thank you, sir, for organizing such sessions.
Thank you, Shikha.
Hello, sir.
Yes.
Jiya Verma from 𝕸𝕤𝕦𝕤 Guriarpan College, Kozhikode. And this section was so informative. And thank you, ma'am, for conducting this. And thank you, Vinod sir, for organizing this. Thank you so much, sir.
Thank you, Nandana.
Hello, ma'am.
Hello.
Happy to see you again. I am 𝕨𝕤𝕦𝕤 from St. Teresa's College, 𝕨𝕒𝕥𝕙. The session was very much helpful during our last lab towards the TIFR exams. And some of our topics was new for us, but still you handled it very nicely. Thank you, sir, for organizing the session. Once again, thank you, ma'am.
Thank you, Harita. Yes, others.
Hello, ma'am. I'm Gayatri. I've done my graduation from Miranda House College, Delhi. The class was really nice, ma'am. The questions that you have discussed were really useful. Thank you so much for taking a class, ma'am. Thank you.
Gayatri. Yes, others.
Good afternoon, ma'am. Myself, Shilpa. Thank you, ma'am, for spending your valuable time with us. The session was very much informative, and it would be very helpful for many of us for our upcoming examinations. And thank you, Vinod sir, for organizing such a wonderful session. Thank you.
Thank you, Shilpa.
Hello, ma'am. I'm Malavika, third year BSc Math student of 𝕸𝕤𝕦𝕤 Guriarpan College, Kozhikode. Thank you, ma'am, for this wonderful session. It is really helpful for us, and it is very interesting also. Thank you, ma'am, for sharing your valuable time with us. And also, I would like to thank Vinod sir for conducting such a wonderful session for us. Thank you, sir and ma'am.
Thank you, Malavika.
Hi, ma'am. My name is Zahra, and I'm from PMG College, Tirur. And thank you for your valuable section. Very interesting. And thank you, sir, for conducting this section. Thank you.
Thank you, Sarah. Others?
Hello, ma'am. I am TT Bijumon for NHP.
How are you?
Ma'am, I am good. How are you?
Fine, fine.
Yeah, ma'am. Ma'am, today's session was very nice, and it will be help us for a NET gate for our upcoming exams. So thank you so much for conducting this session. It is very useful for us. Thank you, ma'am.
Oh, sure. Welcome.
Yes, any others?
Hi, sir.
Yes, Gopika.
Hello, ma'am. I'm Gopika from 𝕸𝕤𝕦𝕤 Guriarpan College, Kerala. Thank you so much. It's a really nice session. You explained each and every question really well. Thank you so much. And thank you so much for your time and effort. Thank you so much, sir, for conducting this session. Thank you.
Thank you.
Are you outside your home, Gopika?
Hi, ma'am.
Are you outside your home?
Yes, this is my house.
Okay, Gopika. Yes, others?
Hello, ma'am. I'm Anjana from St. Teresa's College, Ernakulam. Today's session was really very helpful for us. Even though some concepts were new, you made it very clear. Thank you for your time and effort. And thank you, Vinod sir, for organizing this session for us.
Yeah, thank you, Anjana. Okay. Yes, Andrew, sir.
Hello, ma'am. Thank you for this session. First of all, I am Andresa Sebastian from Assumption College, Chennai. It was a very good session, and there were some new topics, but you explained everything with clarity. Thank you for your valuable time. Thank you, sir, for conducting the session.
Yes.
Hello, ma'am. I am Lakshmi. I am from PMG College, Tirur. Today's class was really nice and interesting. You explained each topic very clearly. And thank you, ma'am, for spending your valuable time with us. And thank you, Vinod sir, for conducting this class. Thank you.
Thank you, ma'am, for spending your valuable time with us. Thank you, sir, for conducting this class.
Okay, bye. See you.
Okay, let us wind up here.